Hi, I just wanted to take a little bit of time and discuss some of the problems that are in the pre-calculus review homework, specifically looking at, this is part 2, looking at the trigonometry problems. One of the things I'm going to be referencing a lot, and I hope you can see this, is this front cover table of trigonometric kind of formulas. Like I said, if you have the hard copy of this textbook, it's in that front flap. If you don't, I will post a copy of this and you can see it. It's also in kind of like a formula sheet on the electronic version, but I'll try and get this to you. It's just kind of a summary of a lot of different trig functions that you can see. Theorems and properties. So when I'm looking at this first problem, it says find all angles which satisfy the following equation. Tangent of theta equals the negative of the square root of 3. So one of the things that we have to consider when we're looking at this is a lot of times people want to solve this for theta by taking the tangent inverse of both sides. And that is perfectly fine to do. The only thing that becomes problematic is because the tangent inverse is actually, let me write this correctly, the tangent inverse is not quite the inverse of the tangent function. So the tangent function, if you were to look at it, it's not one-to-one. So that means that some inputs, for the same input, you can get the same output. That goes for any of the trigonometric functions. So when we talk about their inverse, we say, hey, just look at this restricted domain of the tangent function or the cosine function or the sine function. And then when we talk about its inverse, well, then it's, since we have a restricted domain on the standard trigonometric function, the inverse trigonometric function is going to have that restricted range, restricted output. Okay, so we can certainly do this to find theta. However, we are making an assumption at that point then that theta is in a restricted area. And technically there's infinitely many ways that you can get infinitely many thetas that can give you an output of negative square root 3. So when we talk about, what kind of theta values, if we just use the simple tangent function, you're going to get one value, and that's because the inverse tangent function is working with a restricted range. We want to consider it for all possibilities. So there's a lot of different ways. One of the first things that I would do then is I would pull up a unit circle, and I take into account that tangent is sine theta over cosine theta. And so I just look at, where do I get negative square root 3 then, if I consider that? If I do sine divided by cosine. And so I'm using this unit circle, and ideally I would pull it up. But when I look at this, so sine is the y value, so I know that I want to have sine on top, and I want specifically the difference to be negative. So 1/2. And what I come up with is theta equaling, well, one of the first ones is that 2 pi over 3. If theta equals 2 pi over 3, well, that's certainly going to get me on the unit circle. And again, I can't show you this formula, but that 2 pi over 3, if you look at that, that is certainly going to get me to, that theta of 2 pi over 3 is going to get me the desired output. But at the same time, if I add pi to it, and I get kind of to the other side of the circle, where I have this square root 3, this 11 pi over 6, so I go pi units over the 11 pi over 6, I'm still going to get, if I take tangent of 11 pi over 6, I'm still going to get that output of negative square root 3. And then if I go 2 pi rotations, I'm back to this point. Granted, my theta is 2 pi greater. If I go another pi, I'm here. And so every pi rotation, I'm kind of hitting that point again. And so that's where, again, if you graph the tangent function, it's not one-to-one. There's infinitely many theta values that get you that output of square root of 3. So instead of just listing one explicit value, we say, hey, let's come up with a formula. And so we know that 2 pi over 3, and then any pi multiple of that. So if we go, from 2/3 pi, add pi to it, we get 11/3 pi. Okay, well, if we go that rotation on the circle, that's also going to get us that negative square root 3. And then if we go another, we're going to get that negative square root 3. So we end up with this saying, 2 pi over 3, and then any pi rotation. So if you did, 1 pi rotation, okay, you get that 11/6, excuse me, I keep saying 11/3, 11/6 pi, spot, and you still get that square root of 3. Another pi rotation, you're back up to that 2 pi over 3, or, a 360 added on to that, but you're still in that same spot of the unit circle. So for this, then we end up with the answer being 2 pi over 3 plus pi over k. For this one, we want to give the exact solutions. And this one is saying, hey, certainly there's infinitely many values of x that would satisfy this equation, but we're only looking at the ones between 0 and 2 pi. And that's really nice, because from there, then I can go on my unit circle. In my unit circle, one rotation is from 0 to 2 pi, so I don't have to consider things outside of that. So I look at, then, where do I have sine and cosine being equal? And that's going to be for pi over 4 and 5 pi over 4. Now, in the previous example, we said also any pi multiple of that. So, if you go 1 pi over, 2 pi over, you're still going to keep ending up on those same points on the unit circle, but we're only looking at the ones between 0 and 2 pi. So that's where we just end up with pi over 4. So for solving this one, there's a couple different ways that we could look at this. We want cosine cubed of x to equal cosine of negative cosine of x. Okay. So we could look at cosine to the third of x or cosine of x cubed. When does that equal negative cosine of x? So one of the things is, if I take a value and I raise it to the third power, of course, it's still going to retain that sign. I'm really looking at, where does cosine of x, regardless of if I raise it to different multiples, where does it still equal cosine of x? And so if I'm looking at cosine of x being, 1/2, if I take in cube 1/2, that's no longer going to be 1/2. But if I take values like 0 or 1, then if I cube 1 or if I cube 0, that's going to get me where I want to go. And that sign of the negative there is also taken into consideration. So when I go on my unit circle, the x values that I'm going to focus in on are when cosine of x equals, when x equals 0, when that theta equals 0. And then here, cosine of x is going to be 1, and cosine of 0 is 1, so this is going to be -1, so they're not equal at 0. But that's kind of one of the ones that we would expect. If you square 1, you're going to have that same value. And I apologize, I don't know why this. No. I wonder if it just died on me. Yeah, I think it did. Okay. Well, let me just pause the video here and get let me get a. Okay, and we're back to recording, and I've got a pen that works, so this is great. So thanks for your patience. So back to where we were, we had 0. We considered what if x is equal to 0, and when we do that, we would have 1 to the third, which doesn't equal the negative of that. So certainly 0, while being kind of I don't want to say a multiplicative identity, but if you raise it to a power, it doesn't change its value like 1. We do want it to change or have the same value that it retains its sign. And 0 doesn't have a sign, so we won't consider that one. So this is just crossing off 0. The next one that I see being of interest is x equaling pi over 2. When I take x equaling pi over 2, well, cosine of pi over 2 is going to be 0. And cosine of pi over 2 is going to be negative 0, but 0 doesn't have a sign. So this actually does hold true. The other value that kind of becomes interesting is pi. So cosine of pi, using my unit circle, is negative 1. And then cosine of pi is negative 1. Well, that negative out front, then they no longer equal. So we cross off that value, it doesn't work. And then the last value, well, there's kind of 2 more that I would consider, but that 3 pi over 2, when I go to the unit circle, cosine of 3 pi over 2 is negative 1. Negative 1 to the third is still negative 1. And then cosine of 3 pi over 2 with that negative is still going to be a negative 1. So these end up being the 2 that work. You can check 2 pi. It doesn't work, but also it's not within that interval, so it's not one that we consider. So we end up with x equaling pi and 3 pi over 2. This last problem isn't a trigonometry problem. It deals with algebra, but it's really important for our definition of limits. So I'm just going to go over this here. So here I want to evaluate this expression, and I'm given this function right here. And I should sort, and I didn't realize this was going to be such a colorful. So the things that are interesting, I have this point, f of x plus h. I'm not given that. I have f of x. Oops, again, I just don't want it that large. Switch colors. We have this f of x, okay, which we are given. This is our f of x right here. And then the last thing is we have h, and we're given h. So I like to just kind of go through, so we're given h here. And I like to just say, okay, well, let's combine and make sure we have all these parts. And I don't want, so this f of x plus h here, if I input, I'm replacing x with x plus h. So I'm going to do that here on the right hand side. So I have that negative out front. I have this x plus h quantity squared plus 3 times the quantity x plus h minus 6. From here, of course, the order of operations, I'm going to apply the exponent first. X plus h times x plus h, we're going to FOIL or recursively distribute, however you want to think about that. But we get x squared plus 2xh plus h squared. We'll distribute the negative next because subtraction comes after. And then I have this 3, and I can distribute that. So I get plus 3, move this over, 3x plus 3h minus 6. And then from here, I distribute this negative. I get negative x squared minus 2xh minus h squared plus 3x plus 3h minus 6. Okay, so that becomes our top part. And then f of x we're given. So let's go ahead and look at what we all have. So when I look at this expression, I simplify that f of x plus h. I can input this expression here. I have negative x squared minus 2xh minus h squared plus 3x plus 3h minus 6. Put this because it's going to get lengthy. And then I have, so I could put parentheses around this. I don't necessarily need to because there's no coefficient out front, but you can. And then I have a minus. And then here I'm going to put this f of x, and f of x is equal to negative x squared plus 3x minus 6. And notice again right here, I used parentheses. This one you do want to use parentheses because you're subtracting everything. You're subtracting everything that is f of x. So you're going to subtract all of those terms. And then for h, we have h over that. Okay. So then I just simplify this expression. And one of the first ways I'm going to simplify this is just distributing that negative to each of those terms. So I'll leave this negative x squared plus 2xh minus h squared plus 3x plus 3h minus 6, and then I'll distribute that negative. So I get plus x squared minus 3x plus 6 all together over h. And then I look at, okay, well, let's cross off our like terms and simplify that numerator. So I have minus x squared and plus x squared. I'm going to have this 2xh, this h squared. The 3x and the 3x are going to cancel, and that minus 6 and that plus 6 are going to cancel. So when I do that, what I'm left with is I have this plus 2xh minus h squared plus 3h all together over h. Here we can factor out an h. So I have 2x minus h plus 3 all together over h. Then we just want to make the claim that h does not equal 0. And of course, that's kind of given in the directions when they put h in the denominator of the fraction. We can assume that. We're not making a huge leap by assuming that. But when we do that, then we're left with 2x minus h plus 3. Okay. One of the things you're going to start to encounter as you do more of these, if you recognize a pattern, it's going to be that the x terms are going to cancel when you get to this step right here. So that's something that you'll take into consideration. And then later on, we're going to look at, well, what happens if h was 0 or h gets close to 0? And that's something you can expect as we progress through this course. All right. Thank you.